Okay, so we left that off our last video at the point where we now perform calculations according to our equations that we found, and we find all the variables according to the equations in this loop right here. At this point, after this, our second task is to graph them, and there are three different graphs that we have to produce. First graph is we hold xi and FSB constant while we plot NP versus a varying YP from 0.01 to 1. What this means is that if the user even enters a vector for, say, for FSB and xi, we will take the average of those two to keep them as a constant value. And we will generate a vector of variable length from 0.01 to 1, increments of 0.05, and then we will find how that change relates to the number of moles of ammonia produced. Once we calculate that, we graph that on a graph and on a plot, and then we see how that affects that equation for ammonia production. Our second graph holds the variable xi and yp constant, and it plots the number of moles of ammonia produced versus the variable FSP, which is in a range from 0.01 to 1. Same situation, we take the average of the other two variables that we are keeping constant, and we make a range vector from 0.01 to 1 for FSP that we are changing, and we use that to calculate the number of moles and see with that graph we will be able to see how the variable FSP affects the number of moles of ammonia produced. All this right here is the same as before. We use that equation and we compare the two as a polyfit equation. We come up with a linear equation that relates them together, and then we graph them. We graph the data sets and we graph the trend line for those variables over here. When this is the trend line, this is the variable, and once we see that, then we will see how those relate to the change in ammonia production. Our third graph holds FSP and YP constant and varies xi naught from 0 to 0.99 versus number of moles of ammonia. So in essence, what's happening is we are comparing the three variables that the user enters against the number of moles of ammonia produced to find out which option will be the best to minimize and which variable will be the best to maximize. This way, when we find the best possible way that we can get the most ammonia produced without reducing many resources. So once we do that, then our task 3 is to recommend optimized conditions based on those graphs. So first, at this time, I will run this code, and I will run this part of the code, and I will show you the graphs. Go back here, and run. Okay. Now, those figures are supposed to be separate, but right now for this video, I've put them all together. I believe it makes it a lot easier to see. When we maximize this, you can see that when we graph NP versus YP, the most ammonia moles produced happens when YP is at its lowest point, right over here. Now over here, when we graph FSP and NP, we can see that the reverse of that situation is happening over here, where when we have the most FSP, the highest number for FSP is when we get the highest number of moles of ammonia. Over here, when we graph xi naught and NP, we see that the number of moles of ammonia is highest when Xi naught is its lowest value. Now this, if we go back to our equation, which is right here, we should be able to see that number of moles of ammonia produced is 2 times FSP N1. If we sub that, if we use N1 that we calculated over here, right here, if we sub that back into this equation, we can see that FSP ends up in a numerator and that YP and Xi naught must be minimized in order to maximize NP. I believe I have this up here, which is a lot easier to see. If you see that right over here, this equation is where you can see it much more clearly, where Xi naught must be least and YP must be its lowest value to get the highest number of moles of ammonia. So we go back to our graphs and we can tell the user that, hey, this is the best possible way to maximize ammonia by increasing the value for FSP and reducing the value for YP and Xi naught. So in order to find the highest number of moles of ammonia produced, we go back to our code. Right here, this is task 3, where we use the minimum value for YP entered by the user and the minimum value for Xi entered by the user, and then the maximum value of FSP entered by the user, and we find the maximum number of moles of ammonia that theoretically that it would produce based off of our equations. So in this scenario, our randomly generated values are for Xi were this vector right here, 1/7, and YP was this right here, and FSP was this. So let's say, for example, if a user enters all these values, and so we come up with number of moles of ammonia of that value. So what we've done in this code, in this part of our code, is we've taken the minimum value of Xi naught and we've taken the minimum value of YP, and then we've taken the maximum value of FSP, and then we plug them into our equation to find the highest number of moles of ammonia that the user will produce, which is displayed on our command window right here. Maximum number of moles of ammonia, 3.37. So each time the code is run, the user will enter different values for these, and they will be able to see different graphs, and they will be able to find out how much ammonia they are producing by each value they can find. So let's say if we do another run, we can find similar situation where number of moles of ammonia is highest when Xi naught and YP are lowest, and number of moles of ammonia is highest when FSP is highest, and at this point the user will produce about 0.483 moles based on their values, which are changing. For us, they're changing randomly, but when the user will run this, I will delete these random vectors and I will make them run that, and I will make the user enter the values. So let's say if I can do that on the video if you like. Say if we do this and we cancel that. Before we enter, I will do that. Now our second task, or fourth, keeping count, our fourth task was to find the utility cost, and these values are also entered by the user, and this section of the program is run